So what we're going to do is we're going to simulate a Legate system, which is essentially two links. So you can think of it as a double pendulum, but turns out that the double pendulum, when you put it in the right configuration, can actually walk. And so here's how you can build a walker based on a double pendulum. So if you get the initial conditions just right, then this walker walks downhill. So that table is actually sloped downwards, and those the gray patches are actually what is known as stepping stones. So when you walk, or when I walk, or humans walk, we basically don't have an issue of stubbing our foot on the ground when we swing our leg, and that's because we bend our knees. This particular walker doesn't have any mechanisms to bend its knee because it doesn't have knees. So it's basically straight-legged walker. And so you need to have these stepping stones so that the leg can swing freely and not stub against the ground. Okay, so dynamic walker, and the reason it's called passive dynamic walking is because there are no actuators, no motors getting the system to walk. So one of the easiest ways we can think about walking is to actually design the system so that it's able to walk without control. So once we can do that, then it's easier to add a actuator and then make the robot to work much better than what it walks without motors. So instead of obsessing with control right now, I will show you how to use or model the system. And then later on in the course, we'll actually do control. Okay, but this is a precursor to doing that. One of the secret sauces behind getting this robot to walk is that it's actually not walking on level ground, it's actually walking on a tilted floor, and that tilted floor give the robot energy to move downhill. So this is a ramp, then the walker. This is one leg, and then let me draw the other leg slightly lighter. Okay, so what I'm going to do is I'm going to try to understand the system just like I tried to understand the bouncing ball system. So first, let's say that the robot is such that the foot just hits the ground. So this is called foot strike. Okay. Once that happens, what needs to happen is you need to switch the legs. So now this leg, which hit the ground, is going to stick to the ground, and the other leg is going to swing freely. It should have been touching. So this ground, the leg which is on the ground is called as the stance leg, and the one which is swinging is called the swing leg. Okay, and so it's going to freely move. Eventually, you know what? Let me change the color. It might make it easier to understand this. Okay, so the red leg is the swing leg. It swings, eventually it swings past the stance leg. So let's try it this way. So here it's about to hit the ground. And then finally, it just hits the ground. And we have foot strike. So this is how the system works. So this is next, then it goes here and goes here. And then if you want to keep moving, then this ties back to this one. Okay, at the foot strike part, both legs are touching the ramp. Well, this will become clear in the modeling. What happens is really when the front foot hits the ground, this one immediately releases. Okay, this is an assumption we'll make. So when humans walk, we don't quite do that. What happens is both our legs are on the ground for an extended period of time. It's about 30, 40 milliseconds. In this case, we're going to assume that when the front foot hits the ground, the back leg immediately releases. Okay, and that'll become clear in the modeling. So you can see that just like we had this one bounce, which was one discrete repeating unit, we have this repeating unit consisting of single stance phase where one leg is on the ground, other leg is swinging, and then the foot hits the ground. So that's the foot strike phase. And so you keep repeating these two and you get one step. So this is what I shown you pictorially is one step. And I'm going to now write that equation I wrote down earlier for the bouncing ball, but the same thing for the double link walker. So here's how we'll do it. Single stance. So even though I drew so many figures, I don't quite need so many things in the equation to describe that. So single stance, detect, ground. Okay, so that's where you can see the foot strike. So then there's foot strike. Then a single stance, foot strike. So you can see that the repeating unit is right here. Single stance, foot strike. One step or the repeating unit. So as long as we can simulate one step, we can then call it for 5 steps, 10 steps, or even 5 seconds, 10 seconds, and see the simulation take those many steps. So that's the key, is to simulate one step. So in order to simulate one step, we need two things. One is we need to write equations for single stance. So this is exactly like a double pendulum, except that the double pendulum is in a slightly different configuration. The equations are going to look very similar. And then the other phase is equations for foot strike. Okay, and these equations actually come from the Newton-Euler's equation by, Euler-Lagrange equation by doing some, taking some limits as time t goes to 0. Okay, and we'll see how to do that. Okay, so next part now is to first write the equations for both these phases. Once we have them, we can put them in Matlab and do the simulation. So let's try to get these equations. Okay, I just have 2 minutes. So I'm going to set up the system, the caricature of the system with angles, and then I'll stop. Okay, so the way I'll model the system is I'm going to show the ramp as level, and that's because I'm going to write all the equations on with a reference frame which is fixed to the ramp. So this is going to be my x0, y0. Okay, the ramp is something like this, right? So I'm just tilting it to make it easy for me. And then robot is, or the two-link pendulum is going to be something like this. Okay, I'm using this convention because this is the normal convention people use to derive the equations. Okay, and then I'm going to assume there's a mass at the, this is like a torso mass. Your whole body is replaced by a mass at the connection between the two links. Each leg has a mass. And let's call this C1, C2, H, G2, G1. And then the slope is gamma. And then there's gravity. Let's call this mass capital M, this small m, inertia I. So this is actually a point mass. We'll assume there's no inertia there. Okay, so it's 1050. I'll stop here, but next class, I'll basically set up the Newton Euler Lagrange equations for this by going through the same process we've used in the past. So these figures get cluttered pretty fast. So what I'm going to do is I'm going to draw multiple figures for multiple things. So here is a figure which shows all the mass parameters and also the geometry, right? All lengths, mass, inertia, ramp slope, gravity, and so on. I'm going to draw another figure for the frames, which I'll be using to derive the velocity and positions of different points in systems. So here are the frames. Okay, I don't quite need to draw the masses here, so I'm going to skip that. So first of all, I need a frame which is attached to the ground. And as I said here, it makes more sense to define a frame which is along the ramp. Okay, so this is going to be my base frame or fixed frame. Okay, now let me draw a frame for the first leg, which is this one. Okay, and then I can draw a frame for the second leg. Okay, so I've sort of tilted the whole figure such that the ramp is actually flat. I also need a frame to describe the slope, which is, now in this case is going to be at an angle. So I'm going to draw that like so. And let me call that xg, yg. So normally when you look at walking on flat ground, your xg, yg will coincide with x0, y0. In this case, it's not going to coincide. And if you like, I can just redraw x0, y0 just to show you how they would line up. Okay, so let me now try to write the angles as I would write when I did the rotation translation formula. So if you remember, when I wrote the, so let me put recap. So this is going back to probably the first few lectures where I said that theta is always going to be the angle between x0 and x1. Okay, or it can also be the angle between y0 and y1. So I need to take this particular framework and apply the same thing on this figure. So what I'm going to do is I'm going to now write the angles as they are from the recap. Okay, so I describe the angle theta1 as this one, right? That's just some angle in the system. I need to figure out eventually what is the angle between x0 and x1, because that's how it is defined in my original figure, which is used to get the rotation and translation formula. Okay, so here is a bit of geometry. So if this is theta1, then this is theta1, right? And then this is going to be hold on, I believe I made a mistake here. uh, it's always okay. So when we talked about pendulum, remember we always express the frame x along the link length, and y to be normal. So x1 y1. Okay. And here I sort of violated that. I actually drew y1 to be along the link length. So let me not do that, just to make it consistent. So what I'm going to do is, all I need to do is erase this, because x1 is no longer along perpendicular to the link length. So let me call this x1. Okay, and I'm free to define x1 y1 the way I want. And then y1 should always be at right angles, such that if you remember the right hand rule, if you curl your fingers from x1 to y1, the thumb should give you the direction of the k direction, or the third direction. Okay, so this is more consistent with this. Okay, so now let me now find out what this angle between x0 and x1 is. So you can see now that that angle is simply 90 plus theta 1. So between x0 and x1, the angle is pi by 2 plus theta 1. Okay, so 90 plus theta 1. Next, I need to find the angle between x1 and x2. So x1 is now, I'm just going to extend this line. That's simply x1, and x2 is this way. Okay, and I already described theta 2 to be the angle between the two legs. So again, I need to find this angle, x2 and x1. So you can see that this line here is a straight line. So this angle is 180 degrees. And so this angle has to be 180 minus theta 2. Or in other words, if you sum this angle, 180 minus theta 2, with this theta 2, then you end up with 180 degrees, and that's what that complete angle is. So the angle between x1 and x2 is pi minus theta 2. Okay, is that clear? That might be a bit confusing. I'm just trying to make this consistent with some other notations I have to use consistently for Legate systems. If it's not clear, I can re-explain. Anybody wants me to re-explain anything? Okay, so let me move on. So because I have already defined these angles, now I can write R10. So R10 is simply cosine of the angle between x0 and x1. So that's cosine pi by 2 plus theta 1 minus sine pi divided by 2 plus theta 1 sine pi by 2 plus theta 1 and cosine pi by 2 plus theta 1. Okay, and R21 equals, again, this is going to be the angle between x1 and x2. So cosine pi minus theta 2 minus sine pi minus theta 2 sine pi minus theta 2 and cosine pi minus theta 2. So once I found these angles x0, x1, which was kind of complicated, but that made my life easy when it came to writing R10 and R20, because once I have those, it's kind of simple to write the positions of different things. So with this, I'm going to now proceed to use the Euler Lagrange method. Okay, so basically those 4 steps in that framework. So I'm going to let me just redraw it again in the next page. Okay, so here is the drawing. H, G2, C2. And I really don't need to draw thetas now because I already have that's in the R1 and R10 and R20, R21. Okay, so now we know that the way this walker works is C1 is grounded, right? And then it will move like a double pendulum effectively. And then when C2 makes contact with the ground, that C2 is anchored to the ground and C1 is free to swing. And so the anchor point keeps switching between C1 and C2. Okay, and so that's a little bit more complicated than a double pendulum. And so to make this more generic and to sort of make my life easy, I'm going to do this derivation in a slightly more generic way. So this is what is known as a floating base model. And it's called floating base because instead of anchoring C1, I will not anchor it to the ground. I'll actually say that the position of C1 is x comma y, where x comma y is going to change. So if it's anchored to the ground, then y will be 0. If it's not anchored to the ground, then y can change, right? So let's call that xy. So that's the floating base. So that's not at 0 comma 0 like we would have in a double pendulum. And now all I need to do is describe the geometry or the positions of the different points using some of the formulas we've developed for translation rotation. So let's start. RC1 in frame 0 is simply XC1, YC1 if you like, which is nothing but X and Y. Next, I need to describe the position of G1 in frame 0, and that is going to be, so for RG1, I need to first get the position of RC1, and since C1H is described by the frame 1, I would have R10 times, so let me put the frame here, X1, X2, and then if you remember this was C is the length between H and G1. C, and then the other length which you need to know is the length of the leg, which is L. Okay, now I'm set. So this is going to be R10 times the distance from C1 to G1 in frame 1. Okay, so in frame 1, which I've shown here, the distance is clearly the length L minus C. So L minus C along the x-axis, and the y-axis which is shown here, the length is 0. So this is distance along frame x1, y1. So what remains to be done is to sub in the formulas for R10, which I wrote down on the earlier page, and I don't recommend doing this by hand. You can use Matlab to do it, and that's what I'll be doing later on. So then we can find the position of RH0, and if you look at the figure, that is follows from G1. You essentially have to do the same thing as G1, so it'll be RC10 plus R10 times the distance of H from C1 in frame 1. So that's going to be L for the X and 0 for the Y. Okay, so let's keep doing this. Let's get RG2 in frame 0, which is now this point. And so that position is going to be RH0 plus, it'll be R21 times RG2 in frame 2. Okay, I'm just breaking it down to 2 steps. So this is how you can write it, but you can also write a formula for RG. So this is RH0 plus, my bad. Okay, my bad. I should probably write it slightly differently. This should be RG2 in frame 1 times R10, right? So this is just formula following the same recipe as this one. Okay, but RG2 is R21 RG2 frame 2. That's slightly better. Okay, so I can't just jump from 0 to 2, which I tried to do and which was incorrect. So I go from 0 to 1, and once I wrote formula for 1, I can then sub in the formula for 1 in terms of frame 2. So now I can write RH0 plus R10 R21 times the distance of G2 in frame 2, which I know from the figure. It's simply this distance from H to G2. Simply C and 0. Okay, and then finally I need to find the position of C2, which you can see is here, and that will have the same formula as G2, except that the length of C2 in frame 2 is going to be L. So RH0 plus R10 R21 L and 0. Okay, any questions so far? So this by far is the most involved calculation we've done so far, because there are so many points and um, quite similar frames as the double pendulum, but it's still slightly involved. Okay, no questions, let me move on. So I've been able to describe the positions of different points. Now I also need to describe the position or relate the frame, which is the ramp frame, with the frame which is along the ground. So what I mean by that is, I do have the ramp, and I've made the ramp horizontal just to derive the equations, but really everything is in the base frame. And so let me call this frame, say really xg, yg, and then this is x0, y0. So when you write the potential energy of the system, you need to write it in the ground frame. You cannot write it in the frame 0, because frame 0 is the ramp frame. So I need to find the conversion from ground frame to the base frame. So what I'll do is, so this angle is gamma, or this angle is gamma, and the formula is essentially, if you had any vector in base frame and you wanted to write that in the ground frame, then since the ground frame is at an angle to the base frame and this is gamma, so you'll have R of gamma, where R of gamma is cosine gamma minus sine gamma cosine gamma. However, what we're trying to do here is we're trying to do the opposite thing, which is we're trying to find the positions in ground frame given the positions in base frame. So it's going to be this. So this thing here is simply cosine. So there's a property which is R of gamma inverse is equal to I, right? And so it turns out that from that, R gamma inverse is cosine minus gamma minus sine minus gamma sine gamma cosine, sorry, minus gamma. Okay, so I need this formula, which I'll be using in my derivation. Okay, so this is all the work I need to do in order to find, so this, so far we have R G1 in frame 0, we have R G2 in frame 0, we have R, H in frame 0. We also need position of R G1 in frame G, R G2 in frame G, R H in frame G, and that comes from this formula. Okay, so once we have the first items, we can find the second ones in frame G using this transformation. So this means that we've got all the positions which are required in the Euler Lagrange formulation. The second step, or the first step, part B, is to find velocities. So the velocity of G1, for example, is the rate of change of velocity of G1 with respect to time, which you can write it as Gj dq of G1 times q dot, right? So this is, you can either differentiate the expression or use the Jacobian. It'll give you the same answer. So you can do this for VH, VG2. And I will not write this down because it's just going to take so much time to write these formulas down. Instead, I'll use Matlab to do this. Okay, what is the superscript of R sub? This is, superscript is just the inverse. Okay, so let's see how this comes together. So we've got the velocities. Now we have the Euler Lagrange formulation. So for that, we need the kinetic energy. So that's going to be half m is the mass at the hip. So that's going to be m times vh vh0 in the, if you like, x direction square plus vh0 in the y direction square plus half m vg1 in the x direction plus vg1 in the x direction square plus half m vg2 in the x direction square, and 0 is actually for base frame. Let me just skip that. I'm just going to make things look very complicated. Let me just put the square. But here all the velocities are in the base frame. And then I need to write the rotational energy, which is half I1 omega 1 square plus half I1. So in this case, I believe I assume that both legs have the same inertia I. There are two VG1. Yes, good catch. It should be VG1Y. Okay, so what's omega 1? That's theta 1 dot. What's omega 2? It's theta 2 dot. And the reason I have omega 1 here is because the angular speed of the first link is simply theta 1. If you remember, it was theta 1. And then the angle made by the second link, one link, second link, the absolute angle made by the second link with the vertical is theta 1 plus theta 2. And so when I take the angular speed, I need to do theta 1 dot plus theta 2 dot. So this is why this is the sum. Okay. Then we need to write the potential energy. And that potential energy actually has to be with respect to the ground frame, or G, cannot be with respect to the ramp frame. So the potential energy is simply the mass gravity times the y position of h, because this m is associated with h, this is h, in ground frame, plus small m g yg1 in ground frame plus mg yg2 in the ground frame. Okay, so then the Lagrangian is T minus V. Okay, so this, by the way, is going to look pretty complex given that there are three masses which I need to care about, and this is where you just cannot do it by hand. You want to use Matlab. Okay, so that is step 2 of Euler-Lagrange. Now we get to equations. By the way, any questions so far? Okay, no questions. Then step 3, the Euler-Lagrange equations. Okay, so there is a slight detour or sort of slight change from what we've seen so far for Lagrange. So we've seen so far it's d dt dl dq dot minus dl dq. And I said this is equal to 0, and that's for systems where there are no external forces. So we did that for pendulum, we did it for double pendulum. In this case, because we are looking at a system which is a floating base, so again, what is floating base? Instead of anchoring the robot to the ground like we did for a double pendulum, I actually let it float on in the air, right? So C1 is not anchored to the ground. So when there is a system like this, which is floating, and in reality it's not floating, C1 is attached to the ground, I actually need to introduce what is known as a Lagrange multiplier to the Euler-Lagrange equation. So the equation is modified. It's written as gamma, in this case C1, is where I'll have a force, times TF dq. Okay. So what is, this should be J, G, sorry, this should be C1. Okay, so this gamma is known, lambda is known as Lagrange multiplier. Okay, and what it does is basically it basically constrains the system to be anchored. So in this case, this was C1, this was H and C2. So because this is anchored to the ground, there is a force introduced here, and that force, so Lagrange multiplier is essentially a force. So that force ensures that the double pendulum is anchored at C1. Okay, and the way I get this Lagrange multiplier is that I also need to get the Jacobian of point C1 with respect to Q. Now, if you are looking at double stance phase where both legs are anchored to the ground, then you would introduce another Lagrange multiplier. So let's call that lambda C2, and then you modify it as dgC2 dq. So that's, if you want to introduce a third force, let's say that there was drag force, then you'd simply put the drag force, let's say the drag force is here at some point P, and then you'll accordingly introduce that Lagrange multiplier in the equation. So it's very easy to add forces with this formulation. You need the Jacobian, which we talked about, and then the Lagrange multiplier, which is basically a force. Okay, so we've already seen these parts. The Lagrange multiplier is actually an unknown, and so is this one, but you know what the Jacobian is. So what needs to be done is you find the Jacobian, you put it in this equation, and then you know something about, so let me rewrite this formula again, next page. So I write it as d dt dl dq dot minus dl dq equals So let me change the Lagrange multiplier to a force because that's what it is. I think I did a mistake here. My bad. This is not right. This is actually the position of C1. This should be the position of C2. So this is the Jacobian, right, of C1, and this is the Jacobian of C2. Okay, so please correct that. That was incorrect. So you need to take the Lagrange and multiply it with the rate of change of the position with respect to the degrees of freedom, and so that expression is the Jacobian. Okay, so then I get this is equal to the Jacobian. She's the Jacobian transpose of C1 times the force at C1 plus Jacobian of C2 times force of C2. Okay, and so in this case, since we have C1, C2, H, so since C1 is anchored and C2 is free or free to swing, we have F C2 is equal to 0 because there's no force acting at C2. So we can effectively cancel this. We have a second force. We just have two forces. Yes, I wrote it down. I wrote down two forces just to make it generalized, and then I said Fc2 is 0. So you're right, Fc2 is 0. So the second expression just disappears. It'll actually appear later on when we do the Heath-Strike equation. Okay, so finally, the expression looks like this: d dt dl dq dot minus dl dq equals J transpose C1 F C1. That's what we're trying to code, where this is an unknown. So when you derive this expression, what you end up getting is, in Matlab, when you put this down and you simplify things, you end up getting something like this. Okay, so that's just simplifying this part. Okay, where M is going to be a 4 by 4 matrix. Z is going to be X, Y, theta 1, theta 2. B is going to be a 4 by 1 matrix. Since the force is 2 by 1, the Jacobian J is going to be 4 cross 2. Sorry, 2 cross 4, because then the transpose will become, so I'll just set it as 4 cross 2. So it'll all be consistent. Everything will be 4 by 1. Okay. These forces are unknowns, so that's Fx at C1 or Fc1x and Fc2x. Okay, so what needs to be done is, and this is a little bit of rearranging, you need to actually take these two and move them around and write 6 equations. But really, we are not interested in solving for those forces. So what we actually do end up doing is, and I'll show this in Matlab, we do not solve for Fc1x and Fc1y. This should be C1y, sorry. So what was that? Is that theta 1 dot or theta 2 dot? This is theta 1 dot or theta 2 dot. Okay. So this is theta dot, which is going to be theta 1, theta 2, theta 1 dot, theta 2 dot. It'll be a function of many things involving theta ones and theta twos. So it just not be one of them. Okay. Okay, so what happens is, and I'll do the simplification in MATLAB, we actually simplify this to just a 2 by 2 system, such as A theta 1 double dot theta 2 double dot equals B, just like we did for double pendulum. And what helps us to do that is that if you notice, this point here is x comma y. This point is anchored. So if that point is anchored, it doesn't move. And so we will have x double dot equal to y double dot equals 0. So we know that for a fact. So what we can do is we can actually take this first term z double dot, which is so this is true because z double dot equals x double dot y double dot theta 1 double dot theta 2 double dot equals 0 0 theta 1 double dot theta 2 double dot. So those two terms are 0 because the acceleration of the point which is in contact with the ground doesn't move. And so we can actually eliminate two equations. And so we end up with just a 2 by 2 matrix A, a 2 by 1 matrix B, and a 2 by 1. So we eventually end up with just two equations, not four. Okay, and so that makes our life considerably easy. So this is what we'll get in MATLAB.